Okay, let's design the main control unit of the processor. As you can see here, we have the general syntax of the R-type instruction, and here we have the general syntax for the type instruction that can be used for load, store, or branch instructions. If you check them, you will see that for both of them the opcode is always in bits, 21631. This part. And for the art type, we always need to read two registers from the register files, and it can be found from in the field and R field. For the low down store, the Rs is always determined. The base register and the offset is determined by the 16-bit value that we have in the bit between 0 to 15 of the machine code. The only problem is that the station registered for the loading instruction or RT field determine the destination, and for the type instruction or the field determine the destination. So we need a multiple accel in front of the register write index in the register file to select between these two possible options. To select the appropriate register depends on the type of the instruction. For our type R, the fields should determine the target register. For the I type, for the actually load instruction, only the art field should determine the target. So let's add this new multiple accel here. As you can see, the input 0 of the multiple accel comes from the RDF field, and it is appropriate for the art type. And the other input of this multiple accel come from the art field, which is appropriate for the load instruction. So register destination is the name of the control signal of this multiple accel. So if you check it, you will see that we have 9 different control signals in this data path. The registered destination, this one. But just the write ALU source program can source memory write, memory, read or value operation. Op, which is a 2-bit, and MAM to register. These are the control signals that can be controlled by the control unit according to the type of instruction. So control unit check the opcode of the instruction and accordingly set or clear these control signals. So it means that make them 1, unclear means that make them 0. Also these two operations known as the asserted and asserted. This means that make the signal 0 and this one make the signal 1. So register destination should be 0. If you want to select RHT field as the index of the target destination register, and it should be 1 when you want to use R the field as the index of the destination register. Register. Right. If it is 0, it doesn't do anything. But if it is 1 day register on the right register, input is returned with the value on the right. Data input. Look out here. We have a register, right? And we have a write data. Right. Data is a 32-bit data that we are going to save in one of the register. Which one? The one that is determined by the write register. So 5 bits here determine the index of the register that we are going to write data inside it. And the data, actual data, is coming from this bus, the 32-bit data from the write data plus our resource. As you can see, determine the second ALU operand. Is it coming from the register file? If yes, then all users should be 0. If the second operand of the value is coming from the sign extension of the 16-bit immediate data, it should be 1. PC source. It should be 0 if the PC is replaced by the output of the hardware that compute the value of PC plus 4. So in the normal instruction, always we modify the program content or update it by the program plus 4. So for the normal instruction for PC source should be 0. But for the branch instruction, if the condition is satisfied, then the PC source should be 1 in order to make it possible to load the branch target address to the program counter. Memory read and memory write should be 1 if you want to perform the read or write operation from the data memory. And memory to register is another multiple control signal. It should be 0 when the value referred to the registered write data input comes from the ALU and memory. To register should be 1 when the value fit to the register write data input come from the data memory. You can check it. This memory to register should be 1. If it is 1, then the data coming from the memory. So the data that will be saved inside one of the register coming from the memory. And if it is 0, the new result will become stored in the one of the register. So as you can see, we have a control unit and the control unit receives the opcode part of the instruction. Bit between 21,631. These 6 bits coming here and the control unit generate different control signals. The new operation has 2 bits and the other ones are 1-bit control signal. In this table, I summarized the value of the different control signal depends on the different type of instructions. And let me also show you this value in next figure one by one. So this is the data pad for the typing instruction and I wrote the control signal in blue color and I will show you the value of each of them in red color. All users should be 0. The operation comes from the function field of the instruction and it will be depends on the type of instructions that we have in the type we can perform add, subtract and or and some other mathematical or logical operations. So this part or function will determine the value of this operation. The memory, write, and memory should be 0 because we don't need to use the memory. Memory to register should be 0 because we want to select the input 0 of this multiple Excel. The registered destination should be 1 because we are going to use the RV field as the destination. It's me. Active the laser pointer here. OK. So since we are using this field as the destination or the field in the AR type, so we are going to select this input and given to the WN. So the registered destination should be 1. And since we are going to write the data back inside one of the register, the one that is mentioned here, the register write signal should be 1. PS sauce should be 0 because in the normal instruction always program counter will be updated by program content plus for this is program content plus 4 and it's coming here from this input of the multiple Excel coming back and load again inside the program content. Let's take the control signals for the load work instructions. Our source should be 1 this time. The second input of the U coming from this part of the data pattern. I new operation is addition 010 is the addition code. Memory write is 0 because we want to read from the memory in the load in instruction. We want to load data from the memory. So we don't want to write school. Read is 1, write is 0. Memory to register should be 1 because I'm going to select this input and giving back to the register. 5. And register destination should be 0 because our RT field should determine the destination. Again, since we want to write something back to the register. File. Register, write. Should be 1. PS sauce should be 0 like the previous typing instructions because we are going to update the program. Content with program content plus 4. This is for the control signals for this store. Word instruction. Source should be 1. Operation should be addition. We want to write into the memory. So memory write is 1 this time and memory read is 0. Opposite of the load word instruction. Since we don't want to store back something into the register file, this memory to register can be 1 or 0. That there isn't any destination register, so the destination can be 0 or 1. So we consider it as don't care. Also this one is don't care. You don't want to write something inside the register file, so we will put 0 here. So nothing will be stored in the register file. And PC source should be 0. Branch equals. For the branch SQL. The second input of the ALU come from the register file, so ALB source should be 0. The operation that should be performed by the ALU is the subtract. This is the code for the subtract. You don't want to read from the memory or write into the memory. So both of them are 0. The memory register is not used here, so don't care. They just said this initial value is don't care. You don't have anything to write into the register file. So put it to 0. And according to the value of the 0 flag, we will consider to put program counter source equal to 1 or 0. We will put this 1 if the 0 flag is 1, otherwise it will be 0. So by this way, we will branch to the target audience or label if the condition is satisfied. 0 for like equal to 1 means that the condition is satisfied. And finally here I added another multiple Excel for jump instruction. As you can see, the source of the problem, concern now coming from this multiplex. And we have another signal control signal name as John. And what is the input of this multiplex cell? Input 0 is connected to the previous multiplex cell, which is program control plus 4 or branch. The other input of this multiplex cell is the absolute jump address. Let's see how this absolute jumped out. This is computed. This is a 32-bit absolute jump address, but as you can see, 26 speeds, semi-absolute utterance from the instruction. This part actually is coming here. Then we shifted 2 times to the left, or in fact multiply it by 4 or put to 0 in the right side of this data. Now we have a 28-bit semi-absolute utterance and 4 other bits coming from the program counter plus 4, and it is concatenated to this 28 bits. Now we have a 32-bit absolute jump orders. So there is a concatenation here for computing the absolute orders, which should be 32-bit. 4. And it is connected to the input one of these multiple Excel. So this input should be only activated when we have a jump in instruction. So this signal jump should be 1 only for J in instruction, for the other one should be 0. Let me show you the part of the data part that is activated in the something seduction. As you can see here, this 26 speeds, jump orders are coming, then it is shifted 2 times to the left and concatenated with the 4 bits of the program content, plus 4 bits number 28, 29, 30, and 31 before the leftmost nibble of the program, updated program content. By this way, we have a 32-bit absolute jump label auto jump address, and it is given to this multiple Excel. Also check this part. As you can see, the 0 flag is and with the branch signal. Branch should be 1 only when we have branch equal instruction, and for the other instructions should be 0. By this way, we will select the input 1 whenever the branch equal is executed and its condition is satisfied. Both of these two conditions should be 2. Then we will update the program counter from this part, from the computed target address. Otherwise, the program counter will be updated by the program counter plus 4 like the other instructions. Let's consider the control unit of this processor. Control unit is an essential part of the processors, and it manages the functionality of different components of the processor, such as ALU storage units and multiplex servers. Also, it manages the data communications between different components that exist in the data part. For this processor, control unit takes inputs from the instruction of cockpits. As you know, every instruction has 6 bits of code, and this is the input of the control unit. Combination of circuit and control unit generates different control signals. For example, ALU control input, write, enable signals for each storage element and select all controls for each multiple Excel. So in this figure you can see the main control unit, which generates 2 bits control for the value, and also it generates some other control signals for the other components of the processor. But for now, let's focus on the value part. As you can see, the ALU control receives 2 bits from the control unit. You name it. ALU operation, and other 6 bits are coming from the function fields of the instruction. So the ALU control combination circuit generates 3 beats. Its 3 beats are given to the ALU circuit and perform different operations according to this true table. If it is 0, 0, 0, then the function that is performed by the ALU is an. If it is 0, 0, 1, it is. Or if the ALU control input is 0108, operation will be performed by the ALU 110. Subtract 111 set less than So the main control sends a 2-bit oil operation control field to the ALU control. And based on the oil operation and function field of the instruction, the ALU control generates 3 bits of ALU control field. So ALU must perform the following operations. We need add because in the load and store instructions, we need to compute the address of the memory location by adding the base and offset each other. ALU should be able to perform subtract because we need it for the branch instructions. And other operations are necessary for the typing instructions. For example, we are going to implement and or add, subtract, and set lists then instructions. So let's create a table for all of the inputs and outputs of the ALU control. If the instruction opcode is load word, then the control unit generates or value operation to beat has 00. And we don't have function field for the load word. So it is considered as don't care, and this is the desired action that we are going to implement for the load and load word, and as third word we are going to perform addition. So for addition, the new control in port should be 010. So this is the input and this is the output of this ALU control unit. 2 bits coming from the control unit. 6 bits coming from the function field of the instruction. So we don't have function field for load word and a stalwart for the branch. Also, we don't have function field, so they are only half the oil operation, part 00 for load support and support because we want AD, and 01 for the branch equal because we want subtract for the other ones. Our type instruction. The main control generates a value operation equal to 10. So for all of them add, subtract, and or and set less than the oil operation is 10. But the function field is different. This is the function field related to the add, which is 32. This is 34. For the subtract, this is 40. 36 for the, and this is 37 for the old. And this is 632 plus 1042 for the set. Unless. So for each of them, we are going to create one of these numbers, 0, 10, because we want. At the same as this tool, 110, the same as this one. And is 000 or in this ALU is 001 and set unless is 111. So these are the inputs of the circuit and these are the outputs. So there is a truth table you can simplify by Boolean algebra, and find the correspondence circuit for this ALU control combination circuit.